Hi, everyone. Welcome. Appreciate you joining us today. We are going to talk about some fairly technical content, uh, things related to Fluree's architecture, and specifically how Fluree operates under the hood. We'll talk about some of the configuration settings that Fluree allows you to make and why you might consider adjusting some of those default settings. And it's really a talk designed around thinking through scaling the Fluree architecture. Fluree, as probably many of you have seen, you can start up and just run on a laptop, and you don't really have to set a single setting. It just kind of works and you can do things. But of course, considering deployment options, and implications of different choices in that is a whole separate consideration. So we try to, pick great defaults, make things easy to get up and going, but give you the capability to tune and control things for your specific scenarios. And we'll walk through a bunch of those pieces here today. So just really a couple slides to remind everybody what our focus is with Fluree. So Fluree exists to solve the problem of data's increased importance, not only within the organization, but starting to bridge data across organizations. So historically, we've thought about data as being specific to an application, and a database's role is really just state management for an app. The data itself is usually designed by the app developer with no consideration beyond the app itself as far as potential usages. And that's just how we've been building things for a very long time. And it's because everybody wanted the app, the functionality, the workflow. And of course, we're quickly coming into the realm now where the data itself is becoming much more valuable than the app. We're considering data as a critical input. Good data is a critical input to things like AI and ML. We're considering things like customer experiences and reactions to customer events that might require integrating and synchronizing data across partners, suppliers, even customers or edge devices itself. So the role of data has changed a lot. And increasingly, we need to consider structuring and setting up our data so that we can maximize the strategic value of the data. So now it's becoming less about the app being where the value comes from and more about the data. Now, that's not to say that every single application is going to have that consideration, and they certainly won't, but a lot will. Um, what we see happening a lot today inside of organizations is that critical data, maybe data about customers, for example, we are really manually stitching together to try and get more strategic views of. And we're using things like data warehouses, we're doing manual integrations, and we're putting in that effort, which is estimated now consumes about 50% of the average corporate IT budget, is just integrating data and applications. And it's worth spending that money because the data is, again, so valuable. So half of the IT budget is going to it. That's how valuable it is. Yet these still remain sort of workarounds to a problem based on this, siloed approach to data that we've historically had. So what we're really aiming for with Fluree is to allow companies thinking about the strategic value of data to set it up in a manner that can maximize it. How we approach this is Fluree combines a set of standards designed to make data interoperable. So we've started to talk a lot more about Fluree being a zero trust database, which it is and can be configured to be, but also a zero integration database because the standards and the format of the data that we sit on top of or we encourage to be used can be automatically integrated. So it eliminates a lot of that cost in the current IT budgets, just trying to stitch together things internally, and allows data to be merged and combined even across entities and sources without having to expend a lot of energy and effort. And then we also, especially as we think about extending that data outside of our four walls, we need to think about things like trust and security. And that's where a great place for distributed ledger technology and some of the cryptography that is used in that realm can play a really critical role here. So Fluree really marries these two worlds together to allow you to run anything from a micro ledger that's having provable sort of updates to large scale databases that are used only internally to that might be powering traditional apps to data ecosystems where I think everyone is headed towards, where we have interoperable data across multiple organizations. So it's designed to fit a large number of use cases. As I mentioned, we're going to dive into the architecture and how that might impact certain ways to think about deploying Fluree. And to give a high-level overview of the architecture itself, I'll present this diagram, and then we'll jump into a few of these parts to talk about individual considerations of them. So the main two components that make up Fluree are the ledger and the database, the query servers or the query services. Those are really the two primary components. There's other components that stitch in, but they play two very specific roles. The ledger handles updates. It is the only thing that can write to updates and validate updates. And the query servers answer queries. It is the database, if you will. Now, traditional databases make no distinction between these two functions. In fact, a single server does both of these things simultaneously and also limits the scale to whatever limitation on either side you reach. Fluree is designed to allow these two layers to be independent and to scale independently to allow a lot more flexibility. And there's a lot of reasons this just starts to make sense in these modern environments. So the query servers are horizontally scalable. You can truly deploy as many as you want. They can even be embedded in edge devices. So you really have no true scaling limit for database servers. Now, there's considerations for your data itself and different decisions you make that may make scaling this more challenging. Use of smart functions, for example, in Fluree can slow things down. So how you're deploying those and where you're deploying those are considerations to think of. But as it relates to just a standard database, what you would expect a normal database to be, you really have basically a content delivery network, like a CDN-like structure, where these can be deployed anywhere at any time for any duration for any need. And of course, the ledgers where the writes happen, there are definitely more limitations here. So there are going to be limitations on write speed. Fluree makes very strong guarantees about data updates. It has what we call, or what the database world would call, ACID semantics. So it guarantees that data will not be lost. It guarantees that data is either fully committed or not committed. And it's the type of database you're looking for when you want certainty around information. So the structure of kind of pairing these two things as independent services actually allows us to give quite a bit of not only updates and transactional capability on the ledger side, but really powerful analytical capability on the query side. So lots of times in the historical sort of view of databases, you're either going to look at something that's more a transactional based system or an analytical based system. And again, every single technology decision, there's trade-offs between these things. But for many types of apps and needs, Fluree can actually solve both of these use cases in a single solution. So we'll dive in specifically to the ledger, the query service, and then we'll talk about a couple other considerations as it relates to consensus around Raft and also indexing and how that might impact some of the things you want to think about. But we'll start out here with the ledger. So what does the ledger do? As I mentioned, it is the only thing that can handle updates. So its job is to handle writes primarily. And it will go through whatever rules validation you set up. And one of the great things about Fluree is that you can constrain how your data can be updated uh, to do just about anything you want. So there's certain constraints you can deploy at the schema level. You can say some things like multi-cardinality or single cardinality, or you can say this variable has to be an integer or it has to be a string. And then, of course, we allow you to dip into this additional capability of smart functions, which allows you to have programmatic control over what is happening directly within the system. So there's a lot of capability to basically set up a ledger by whatever rules you want. And the nice thing about those smart function rules is they themselves are actually structured as database in or as data in the same database. So all the rules that govern how the data can be updated are just data that can sit alongside of the data itself, which means you can even create rules about how the rules can update. So there's a lot of capability there. What ledgers do is they take an input of transactions. So these are different things that people are trying to, update data with. So these are the transactions coming in, and there's a few different ways they can come in, but transactions coming in. And what it outputs are blocks. And blocks are just deltas to the data that changed as a result of a transaction, along with transactional metadata in the proofs that allow you to guarantee the provenance and integrity of the information. So you can think of the transactions are coming in and it's outputting basically, it's applying those transactions and it's outputting deltas. One thing you will see is that you will see blocks created that are even error blocks. So there might be something faulty within the transaction itself, or that user didn't have permission to change that data based on your smart functions. And Fluree doesn't just outright reject that and sort of ignore that it ever happened. It will even write those errors into the blockchain. But if you actually look at the data inside of that block, what you'll see is no user provided data, but you will see all the metadata that ends up creating that block. So transactions come in, blocks go out. Where do those blocks go? Well, they go a couple places. So one is that if you're running Fluree with local storage, so you're just storing the data on the hard drive of the machine that's running Fluree, it's going to go ahead and save it there. It also is going to broadcast this over consensus. So there may need, depending on your configuration, some amount of agreement that this block has happened and has been committed. And we'll talk a little bit about some consensus considerations in a bit. And then it also is going to broadcast out these new blocks to all the query services that are listening. So all the things that are answering queries are getting updates in real time of these blocks as they're getting created, so that they then can, have current queries. So as whatever app or user is querying that, they can go ahead and run that. The ledger server also is the main source of providing indexing for the database itself. Now, technically, the indexing service does not have to be part of the ledger. It is today. It may be something we allow you to operate independently in the future, but it keeps indexes, which is what allows us to make queries very, very fast. And it does this in the background. But there's some settings that you should think about and know about as it relates to indexing. And we'll talk a little bit about a couple of those. Okay, so one of the things you can do with a ledger server is you can just run it independently. So if you've downloaded Fluree and you run it on your laptop, you're actually running a ledger server and a query server all together. Like, just because we're trying to make it easy, you don't want you to have to worry about deploying these things independently. It's just one thing you're running. Of course, they can run separately. If you choose to run them separately, then what you can also do is run what we call a ledger group. So this is a set of coordinating ledger servers that communicate with each other, that handle consensus work. They also do some other really interesting things, like they balance and rebalance work depending on whether servers are alive or down. And they also redundantly store information if you're using the file system to store the data. So Fluree allows you to store data, for example, even using like object storage on S3. Obviously, if you're storing it on an S3, then you don't need the redundancy of the data on the local disk of these ledger servers. But if you're running Fluree where you're actually storing all the block files on the servers itself, these ledger groups are always creating full copies of all the data that's there. And what that allows, of course, is that a server goes down, you have other servers that can pick up the work. And depending on your configuration, have scenarios where you can have zero downtime. And we'll talk about some thoughts around that as well. So how do you want to run a ledger server? So you make the decision that you're going to deploy query servers and ledger servers independently. You may or may not have a ledger group. How do you actually run this? So you're using, for example, AWS or some cloud service. Ideally, you'll run a ledger server as its own service. What a ledger server does, especially if it is recording data on the file system itself, is it's doing quite a bit of I/O to the disk. And so having fast I/O is advantageous. And there's two different things that Fluree writes to the disk if you're using it for the file system. One is it's writing all the block files and all the actual ledger data. The other thing is it needs to keep a set of log files for the consensus. And it updates those log files very, very frequently. And again, there's some settings that you can change, but even by default, these are getting updated typically multiple times a second. So there's a lot of I/O happening there. So having nice fast disks, you can actually partition the logs data where you're having those frequent writes and updates to files from the ledger data as well. So you don't have to put all these on the same volume. So you can have different characteristics for each of those. And again, some of these things are things to think about depending on your implementation and what you're going for. Can you run a ledger service in containers? Absolutely, you can. In fact, I know we have many customers that do this. Is it the most optimal way of running a ledger server? Probably not. It depends on your circumstance. Part of the issue with containerizing things like databases, and these ledger servers have the same sort of characteristics that you'll see recommendations to ideally not run a database inside of containers. uh, Fluree Ledger has the same kind of components, which is, containers are really, really great for things that have no state. A database inherently has state. It needs to write data to disk. And when you're running containers, you have to deal with, mounting and unmounting volumes. If you're already running Kubernetes in your enterprise or something like that, it probably makes a lot of sense to run Fluree in a container because you're already maintaining that infrastructure. But if you're not already doing that, there's a lot of things that you should know about running a Kubernetes cluster, for example, that could end up impacting Fluree. And if that's not something you have a team running or using every day, then not only do you need to learn the characteristics of running Fluree, but you're also having to learn the characteristics of running Kubernetes. And just even things like permissions. So, volumes that can be mounted and unmounted off of the containers, making sure that Fluree is running as a user that has permission to write. There's just a lot of things you can get hung up on there. But you can absolutely run it in containers. Running it in a container is going to be slower than running it as an independent service. And it's only because in these container environments, even writing to disk has to go through a lot of virtualization services. Um, so generally, if you can just run it on its own sort of virtual machine, great way to run Fluree. It's really designed to run like that, but there's no issue running it in a container. Just different things you need to consider if you choose to do that. Oops. Okay, so before I jump to talk about the query services, I'll spend a minute here talking about running ledger groups in the Raft consensus protocol. So Raft, if you set up a ledger group, it is going to automatically communicate amongst the servers in that ledger group with Raft. Raft is a pretty well-known protocol. It's very similar to Paxos, if you've heard that. There's a number of data management technologies that use Raft, along with a lot of commercial products. Fluree has its own Raft library and implementation that it embeds directly inside of the ledger server. So it runs co-resident inside of the ledger itself. And what does Raft do? At a simple level, the only thing that Raft does is it guarantees ordering of events and consistent state across systems. There's nothing totally, much more complicated than that about Raft. Although how it does this in a distributed environment has a lot of complications, a lot of types of failures that could happen, a lot of things that actually make this problem kind of difficult to achieve. But it's a proven out algorithm that, when implemented correctly, does achieve this event or these characteristics. So when we think about guaranteed ordering, you think about multiple ledger servers. We talked before about transactions coming in and then block data going out. Well, processing those transactions, for example, in a different order will output different results. So we want to make sure that the ledger group is looking at things and has a consistent view, no matter who's looking at it. Which transaction are we working on next? What's in the queue? What are the blocks coming out of the other end? Making sure that all of that is in the proper order and that everyone agrees on the proper order. Consistent state is achieved once every server in the group persistently records an event or an entry in the Raft log. So Raft itself kind of looks like a log of events. And then communicates back to a leader that then says, okay, at least 50% of the network has recorded this on disk. We know it's durable. We know we can sustain a power outage and we'll still have that data. Only then does it accept something is being done. So when these ledger groups are running, there's all this communication happening between these servers, synchronizing everything, doing things like leadership election, et cetera, to make sure that these kind of very simple outcomes are achieved. There's a number of settings in Fluree that these all have defaults, but I'll explain what each of them do because they are things that you might consider changing depending on the environment that you run Fluree in and characteristics of even your database and what you're looking to accomplish. All of these Fluree settings, incidentally, are in our documentation. If you've downloaded Fluree, there'll actually be a properties file. You can set them there. All of these settings you can also set with environment variables, which makes it very friendly to container environments. You can just put, environment variables around the container to control every single setting in there. But you'll see all of the settings that relate to kind of this set of problems that we're talking about here all start with group. So FDB group timeout, FDB group heartbeat, log directory, snapshot threshold, and log history. And a brief explanation of each of these and why you might consider changing them. So the FDB group timeout is a setting that when a server has not heard from a leader in this amount of time, it considers the leader to be down. So the reason you want this relatively short is that if a server truly does go down, you want the other servers to acknowledge that as quickly as possible. The reason that you don't want this too short is that if your servers have latency in their communication, what you're going to end up having is a lot of false negatives. So you're going to have a lot of situations where it thinks the leader's down, but there's just a network delay between the servers and it hasn't happened yet. So by default, I think we ship this with 1 second or maybe a couple seconds, which is, in a very fast, tight network environment, can easily be set even slower than that. There's probably not going to be a lot of good reasons you want this more than 1 or 2 seconds. I could see a scenario where you decide you're going to run 3 ledger servers and you're going to run one in Google Cloud, one in AWS, and one in Microsoft Azure. Obviously, those networks are completely independent of each other. There might be latency as it's going in and out of those. Or you might run 3 ledger servers in different parts of the world. Those may be reasons why you have more network latency, and you might want to bump these settings up. The consequence, if you don't bump those settings up, is that you get a lot of these false negatives. When you get these false negatives, it's not necessarily going to hurt anything or make the system go down, but what it's going to cause is a lot of leader elections. Because what happens is that if a server hasn't heard from a leader in this timeout period, it will assume that leader has gone down. And if it hasn't already heard from a different server in the network that's trying to become a leader and asking for a vote, if it can become a leader, that server itself will request votes from other servers on the network to become a leader. And you'll have a network that's now spending a lot of time doing leadership election unnecessarily instead of processing transactions. So we want most of the work of this Raft network obviously go to ordering, incoming Fluree transactions, outgoing blocks. We don't want it spending a lot of time, doing leadership elections and sort of that administrative work in between. So Fluree ships with a relatively good number here, but you might want to think about bumping that up or down depending on very specific circumstances. The second setting is directly related to the first setting, which is the heartbeat. So generally you want the heartbeat, which is how frequently a leader broadcasts out to the network that it's still alive. Whether it has a new message to deliver or not, it will auto communicate to the whole network in this heartbeat time. And you generally want this heartbeat time to be about half of the time out or even a third of the time out. Because again, you don't want to sort of be on the cusp of these being too similar and you getting a lot of false negatives here. So by default, again, Fluree will set a heartbeat time that's half of the time out, but you can configure this if you need to. The next setting, the log directory, this can allow you to specify a specific directory to use for the consensus logs. Again, there's a lot of writing and updating of files that happens here. So this might be something where if you're running in the cloud, you might have a block store volume that you're using for all the ledger data, because the writes are going to be a little less frequently there, a little bit more bulky, and block storage is going to work pretty darn well for that. Whereas maybe the server you're on has a local SSD drive that it doesn't have to be big, it might be relatively small, but you might actually configure the log directory to use the local SSD drive just to have that extra speed. Again, it's not necessary. We typically even internally are running Fluree like in just using block storage for both of these, and it runs really well. But that might be a consideration you have as far as just getting some more I/O for these logs and consensus. The next two settings, group snapshot threshold and log history, are both related. And what happens is that as Raft is appending entries to the log, those logs can get really big. So what we do is that after a certain number of log entries, we create a snapshot and then just build new log entries from there. So this kind of specifies how many entries in Raft to create before creating a snapshot. Again, very reasonable defaults here. A reason you might consider or think about changing this is that if you had an incredibly high write volume, for example, for ledgers, you're going to be putting out a lot of log entries. And you might want the snapshot threshold to actually be a bigger number, because each time it hits this threshold, it's going to have to open up a whole new file and start writing the new log entries in a new file. So it kind of, if this is 10,000 entries, after the 10,000th entry, it closes out the one log file, starts a new log file, then starts a new log file. So again, great sort of defaults are already set up here for you, but that might be a reason you'd think about changing that. And then the FDB group log history this is just going through and cleaning out old log files that it doesn't need anymore. So you may want to retain a handful of these just in case a log file got corrupt, or server ran out of disk or something like that, and you end up with a inconsistent state. You can always potentially get rid of the most recent Raft file, and then you have other previous versions still there available to you. But again, reasonable defaults here. The other consideration with the ledger group, and this is specific to Raft, although this is going to be consistent with kind of this general class of consensus protocols, is it has a 2F plus 1 failure sort of profile or equation. And what this means is however many failures you want to be able to sustain with zero downtime is F. And if you plug that into the equation, this is how many servers you have to run to sustain that failure profile. So if you want to be able to sustain one server that can be failed at any given time, F is 1, and that means 2F plus 1 is 3. You need to run 3 servers to have one failure with 0 downtime. If you want to have 2 servers that can simultaneously fail with 0 downtime, then F becomes 2, and now you need 5 servers. 3 servers, 3 failing servers, you need 7 servers running in the network to sustain 3 simultaneous failures in the network. So that's how you look at that. This is also the reason you'll see us and really any other product that uses Raft or this kind of class of consensus protocols always recommend running odd numbers of servers. And the only exception might be is if you're choosing between 1 or 2, it's better to run 2. But at the point you're running 3, there's no advantage to running 4 until you get up to 5 servers. So you either want to run 3 servers, you want to run 5, or you want to run 7. Running 4 servers or 6 servers gets you 0 additional benefit. And in fact, actually technically hurts you a little bit because there's more communication that needs to happen because there's more servers communicating. So you're better off running 3 servers than you are 4. You're better off running 5 servers than you are 6, for example. All right, so the query, the database service side. Let's talk a little bit about it and considerations when you think about what it's doing, why it's doing it, and how to think about configuring and running servers. It handles all query execution, and if you're using smart functions, it might even be doing some smart function execution within the query service. Now, we do offer a query service that can run in browser. The version that runs in browser does not execute smart functions, but the JavaScript version of the query service, for example, that runs in Node.js does execute smart functions. So they're just kind of 2 different use cases specifically for that. But it's going to be executing those if you have permission data and you're using Fluree to basically create these kind of virtual databases on a per user basis. So, when a user connects and executes a query, they can cryptographically sign that query to prove who they are. And then Fluree can basically filter the entire database so that that user can only see the data they have permission to. So the query service would be responsible for that type of filtering and smart function execution on the read side. The transactors, which are ledger servers, which we just talked about, execute smart functions, but it's concerned about smart functions as it relates to writes. Do you have permission to update this data, to write this data? Here we're talking about, do you have permission to view the data? And there's scenarios where you may have permission to write data, but you don't have permission to view data. We've come across some of those. So you can make a distinction between these two. The other thing that the query server does when it's handling query execution is it's handling what we call novelty and merging in novelty. And these are the updates to the database that are happening in real time. And we'll talk a little bit about indexing here soon, but you can think about these new blocks coming over as updates are happening. The query services are basically very efficiently able to merge those deltas or those changes into an already indexed set of data. The query server also acts as a proxy. So we talked about transactions already, that the only thing that can process transactions are the ledger servers, but that doesn't mean you can't send a transaction to a query server. And this is more out of convenience. If I'm going to build an app, I don't want to have to point it to like ledger servers and query servers. I just want to point it to one server, and I want to send it updates, and I also want to send it queries. But what the query service does is when it gets a transaction, it just forwards it back to the ledger service, which again is going to be the only thing that technically processes that. And then the results are going to ultimately come back and it'll be able to, respond to the client. This was successful, not successful, or here's the results that happened. A query service can also act as a proxy for other query services. So you can deploy and have a network configuration where you're running query services and then even another layer of query services that don't connect to the ledger servers, but connect to yet other query services. And this can actually fan out. This scenario comes up more than you would think, especially if you're running a set of query services as individual servers. But remember, a query server, well, you may know, I'll talk about this in a minute. You can actually run a query service embedded inside of your application. You know, the idea is that you're actually embedding the entire database into your app. That's a scenario where very often you're running yet another query service, but you're running it then as a library in your application code. Instead of connecting that directly to a ledger server, it's common to connect that to another query service that's actually running as a server. So there's a lot of flexibility here. I started out saying that you really do not have limitations on scale as it relates to query, and part of this is the characteristics or the reasons for that. The other thing the query server is doing is it's managing an in-memory cache. So when you launch a query server, it's going to have a certain amount of memory that it is going to have available to it to store parts of the database in memory for really in-memory query response times if it can hold the data you're interested in. And it's going to be going out and getting data it doesn't already have in memory and bringing it into memory. And then if it consumes all the memory it has available, it's going to start ejecting data out that it hasn't been asked for recently in the form of a query. So it's got to manage all that memory, kind of swapping in and out as it's running. The more memory you have, may or may not be a benefit. It all depends on how big your database is and what your query patterns look like. If most of your queries, which is true of a lot of apps, 95% of the queries are just asking for very recent data. You may have a many terabyte size database, but the apps are commonly just asking for a tiny fraction of that. Fluree tries to organize the data such that it's all together, which means that even though the database may be terabytes in size, most of the query concentration is in a very small hotspot. You may need just a tiny bit of memory in a query service to have basically all the data you need in memory for in-memory speeds, even though the database itself may be huge. Or you may just have a small database that you're managing, in which case you don't need a lot of memory here. So it's not only the size of the database that's going to ultimately determine what an optimal sort of memory footprint for a query service will be, but it's also the query patterns themselves that might dictate that. So those are two considerations to think about. So how does a query service run? It can run as a standalone server or service. And in this case, you're running it as a server. It exposes an HTTP API, and that's how you would interact with it. So whether your app's in Python or whatever you happen to write it in this case, you'd be executing HTTP API requests. In this scenario, it is an excellent candidate for containerization. So before I said that the ledger servers themselves, there's some trade-offs if you decide to containerize it. Here, this is really designed to be containerized. This is how we typically run query services at Fluree. We run them in containers. The query services inherently have no state. They're perfect candidates for containerization. Put them in, Kubernetes or that if you're running it, or even use some great new sort of containerization as a service offerings like AWS's Fargate, for example, is a great option where you don't even need to run sort of an orchestration platform for containers. It can just natively do this. And you can look at our Docker images that we publish for recommendations and ways to run this as well if this is what you're looking to do. Or again, you can run this on a VM directly. This is going to run, in this particular case, it's going to run on the JVM. So really it can run anywhere the JVM can run. You can also run the query as a library, and this brings in the concept of literally embedding the database inside of your application. So Fluree as a library is going to have a certain amount of memory that you allow it to have running inside of your app, and it's going to do this query execution locally. It's like your entire database becomes a local data structure to your code. You can pass around databases as variables to different functions. Flurry's databases are immutable. So once you get a database at a certain moment in time and assign it to a variable, you can literally, handle that just like it's any other data inside of your application. It's really powerful concepts. It really, when you start using this, it really changes the way you code, because you no longer think of a database as this like black box you execute queries to, and then you got to wait a little while for a response to come back from. It becomes a local in-memory data structure you can issue queries against, but you start to be uninhibited to execute even tiny queries, because everything is so fast and in memory that instead of packaging up a bunch of things that maybe you'll need to know but you're not 100% sure into a big query only because you don't want to issue multiple queries, all of a sudden you can just issue tiny queries at incredibly fast speeds. You really truly have the database inside of your code. Um, so as I mentioned, JavaScript is a popular way of running it in this manner today, and we have it where it can run directly in browser, even on like a mobile device. And we also have a Node.js service, which is designed more for you to build a custom app server around the database. So it even allows you to almost create like a custom database interface, because you can wrap your own logic in Node.js, but you have the database right there that you can interact with and issue queries against. A couple considerations here. One is that if you are using JavaScript and sort of this library strategy, JavaScript does not truly support long or 64-bit integers. It only supports 53-bit integers with precision. And the way, and we won't get into sort of how we create flakes and sort of namespace things in Fluree to optimize storage and indexing. We've talked about that before, and we'll probably talk about it here again soon. But what you probably will recall is that everything in Fluree is aliased to an integer to really improve the speed and to keep everything very compact in our storage. What we do is we take that 64-bit integer and we chunk it up, and we allow to keep similar data together, again, for these, for the reasons we talked about before, keeping index segments in memory, but having them have, for example, related data all together. We chunk them up, and we use the first, I think it's 19 bits of the 64 bits to represent a collection or kind of a type of information or a class of information. And then we use, 43 bits, I think it is, 44 bits, to represent each item within that classification. So if we only have 53 bits, now we're only left with about 9 bits in JavaScript that can represent these collections. And if you look at 9 bits, basically that means that anything over 511 collections, which, by the way, I'm not even sure I've seen a database that has more than 511 collections, although I think it's entirely possible that there would be ones that have that. If you go beyond that threshold, all of a sudden JavaScript can't resolve those big numbers. So of course, there's some big number support that you can get into with JavaScript. Big numbers are going to operate a lot more slowly than just standard JavaScript numbers are. So there's some considerations to have there. But just to make you aware of that if you are running the JavaScript library, JavaScript has limitations that we've tried to design around, but something to think about as it relates here. The other consideration is that a query server, wherever you run it, ultimately there needs to be one set of query servers that needs to be able to talk to the ledger servers. So if you decided to completely secure the ledger servers, like behind a firewall, you're going to have to run the query server in a way where it can go through that firewall and basically get access to that. But as you connect additional query services beyond that, of course, now they can just rely on other query services. They do not need that direct access to the ledger server. So that's, depending on how you're thinking about running Fluree, that's something to think about there. Okay, I'm going to talk a little bit about indexing and some considerations here. So, all of these pieces that underpin how Fluree works are designed to allow this really unlimited scale on the query side. And how we approach indexing is probably the most critical part that makes this even possible. So indexing, the reason we do indexing and every database does indexing is because this is how we make queries fast. So if you look at the raw ledger where blocks are created in Fluree, that records all the data as it's changing over time. But if I wanted to search for, what is Kevin's favorite color, if that's all I had to work with, I would have to scan through the entire ledger to find out that answer. And that's going to be really, really slow. So we create indexes that are optimized for answering different types of questions we'll see in queries. And basically what happens is when you issue a query to Fluree, it analyzes that query and tries to figure out which indexes are going to be able to answer the question in the most efficient manner, and it'll go to those indexes. So Fluree creates up to 4 different indexes. We've talked about, some of these indexes, and there's some information in our documentation about the indexes we maintain and what sort of query patterns they're each used for. But for the purposes of here, there's 4 different indexes that ultimately might reorganize data in various ways to make queries very, very fast. The indexes themselves incorporate time, and time for us comes in the form of kind of 2 components. One is what we call the t value, which is the basically an incrementing number for every transaction, and then a block value. And what a block does is it wraps 1 or more transactions together into a single block. So you can always sort of walk through that log by just following that t ordering, and every single, any number of t's may be in a single block. And we allow you to issue queries for any time historically. Well, in order to do this very efficiently, we need to incorporate concepts of time into how we index data. And so most databases do not do this. In fact, almost 0 do. But this is a special kind of indexing strategy that allows us to go through time really just as quickly as we can find other data. So index incorporate time directly into that and can very quickly kind of reify themselves or sort of produce a version of itself at any historical moment in time to answer a query that you wanted to in any historical moment in time. So if you've used time travel in Fluree, you'll notice that if you search for the latest data, there's a good chance that's going to be one of your fastest queries. But if you issue that same query for example, a year ago's data, you're going to see that the difference in speed is almost not discernible. They're extremely close. So time is a first-class citizen in this, and it's very, very efficient. Importantly, indexes are immutable. So when we write out these indexes, we'll never ever change that file. And that's what allows them to be so cacheable upstream. It's what allows, even in a changing database, for query servers, which might be throughout the world, which might be sitting on individual iPhones that apps are sitting into. It's what allows them to hold the data so efficiently in memory because it has a guarantee. Once it pulls data in, Fluree will never, ever, ever change that data from underneath it. So it always knows whether it has the most recent information already local or whether it needs to go get updated information. And I'll talk a little bit about how we do that in a couple settings in Fluree that are worth special consideration when you think about this. So as you're transacting data, we're creating new blocks, and those new blocks come in and they accumulate in memory until we reach 1 or 2 settings. And we call this accumulation of new data, we call this novelty. You'll see us refer to this as novelty very often. So novelty, you can really think of as a bucket. It's like a bucket of water. And new blocks are coming down the pipe, and they're filling up these buckets. And these buckets are running on every single connected query server. So every query server is getting this kind of feed of updates coming in, and it's putting it into its bucket. This data is not yet in a formal index. In indexing, while it can be, especially if your database isn't huge, you'll notice, most indexing processes will be even sub-second to complete. A really, really big database, a terabyte database, could take minutes for it to reindex. Again, it's partially going to depend on the type of data that's in there and what the changes have been. So there's 2 settings that relate to this. And again, we have reasonable defaults in here. You don't have to worry about this unless you're starting to try to optimize Fluree for certain circumstances. But the settings are FDB memory reindex and FDB memory reindex max. And what they are is this first memory reindex is the amount of new data to accumulate before a new index is created. Because again, indexing takes a little while. So we don't want to create a new index with every single update, especially because we can so efficiently merge changes into the existing immutable indexes. There's no reason to. And by doing that, it improves the cacheability upstream because again, if we don't have to change an index, every server automatically knows its data that it already has for parts of the index is current. It doesn't have to ever go fetch more data. So more of the speed can operate in memory. So we want this at a reasonable level, but we don't want this happening like every time there's a new block to reindex data. So we can set a threshold. You set it with a certain size. And this is the threshold that once the bucket fills up to that threshold, it will kick off a reindexing process, but it does it in the background. It's not going to stop transactions or anything like that while that's happening. It's happening in the background. But what if it hasn't finished and our bucket starts to overfill? That's the other setting, is what point do we want to set where the bucket is start overfilling? Because what happens is that bucket starts overfilling, we no longer know if all the query services upstream even have the capacity to hold these changes in memory anymore. So we don't want to send it anymore and potentially have issues upstream. And that's the memory reindex max. So in a typical scenario, you never hit that. You hit this memory index threshold, it'll kick off an indexing process. And before the bucket even fills up much more than that, the new index will be generated. And what happens is as soon as there's a new index, the bucket gets dumped. So the bucket then becomes empty. It can start getting refilled again. If the indexing is taking a long time and a lot more blocks are coming in, our bucket starts overflowing. What happens then? If we hit this threshold here, what happens is the transactors themselves stop processing new transactions until that index process is finished. So when you think about running query servers way upstream, one thing to think about is, am I going to want to run this query server like inside of a web browser? Because a web browser isn't going to have a ton of memory to it. And I'm probably not going to want to keep this memory reindex threshold relatively low because I don't want to blow up the memory in people's web browsers. But if my query servers, for example, I'm all going to run on machines, and the only way anything's going to is dedicated services, and the only thing that's ever going to talk to it is over HTTP interfaces, and I can run those with 2, 10, 64 gigs, whatever I want, then this number can be incredibly high. There's no reason to keep it low because everywhere that needs to cache this data upstream is going to have an immense amount of memory to be able to do that with. Again, we ship Fluree with good defaults. Those defaults really set you up so that you shouldn't have issues running Fluree in a web browser. But if you have a lot of transactions, you might want this a little bit higher. If you don't have that many transactions, you actually might want to bump it down a little bit because data that is indexed is faster. So as fast as we are at merging this novelty in with the already done indexes, if the data is not changing that much, then we might want to set this reindex threshold down. Typical scenario, you don't even have to worry about touching these two things, but all of these components are what ultimately leads to Fluree's architecture, our scalability, and the ability for the speed and the query responses that we see. And then the last thing I wanted to touch on here is the indexes themselves and what those look like and considerations with them. So one thing we do is that in index, and if you've looked at any sort of database indexing, we have a similar structure, a B-tree style structure, where you kind of have this initial pointer at the top, and then it tells you where to go from there if you're looking for certain data. Like, in this simple case, if I'm looking for data, I'm looking for information about Brian. Brian starts with a B. So this index root is going to have kind of pointers to where the B data is. And then that might point me to another branch here which still doesn't have the data, but it then says, okay, well, the B data is this way. And eventually I'm going to get to a leaf which actually contains the data. And then this is where the B data is going to actually end up living. So this is kind of how this indexing happens. What we do specially with indexing to support this kind of caching way out into any device is that we chunk these indexes up into relatively small segments so that they're very efficient to get over HTTP. And each one isn't so big that they're pretty easy to get a bunch of them, even into like a web browser footprint of memory. So we look at about 100 kilobytes. And by average, we find that about 100 kilobytes usually stores about 3,000 pieces of data. So when I got this index segment, because I asked for information about Brian, I not only got information about Brian, I got information about Bob and a whole lot of other people in this kind of segment. And a nice thing is if I turned around and issued a query for information about Bob, this is already in memory now. I don't have to go and fetch any additional data. So when we talked about the query servers being able to manage memory and swap out index segments, this is what they're doing, is that if they pull in a bunch of these index segments and they use up how much memory they have, and another query comes in for data that it doesn't already have in memory, it needs to eject something it does have in memory so that it can make space to bring that new thing in. And it does this with a LRU cache, a least recently used. So to look at the data or the index segment, which wasn't asked for the longest amount of time, and it'll say, well, no one's looked at this for a while, I'll get rid of this and bring something new in. So the more memory the query servers have, the more of these they can hold in memory. Again, they're immutable, so they'll never change. Once we write one, we will never ever update it, which means that if I'm looking for Brian data and it pointed me here, if I already have this in memory, I don't even have to worry that this has been updated. I know it's the same, and then I come over here and I know it's the same. Say we updated data about Brian. Well, once we run an indexing process, we're going to end up having to modify this because data about Brian changed. But if data about, for example, Carl didn't change, this still remains valid and it remains cached in every server anywhere in the world that has this. And it doesn't even have to think about asking if it's still updated. It automatically knows it's updated. But this file is going to have to be updated when we reindex. And then the pointer to that file, because now we have a new file, needs to get updated. And of course, the index root also needs to get updated. So we need to update everything up the tree as well when something updates here. When you think about this as it relates to sizes of database, we use what we call very wide trees. And by wide, what we mean is that each of these nodes has up to 500 children that it can point to, as opposed to a very narrow B tree might only have 2 children, either go right or left, and those are the only choices, and which means you're going to have much deeper trees. So because we have such wide trees, and because each leaf can hold about 3,000 pieces of data, or about 100 kilobyte is what we target, what it means is that a tree that just goes down one level deep can actually hold about 50 megabyte of data. Just one more level, because all these are exponential, we're up to 25 gigabyte. Just 3 levels deep, we're up to a 12.5 terabyte database. And 4 levels deep, we're up in the petabyte range as far as database size. Now, one thing for consideration is, does a 6 petabyte database operate a lot more slowly than a 50 megabyte database? And the answer is yes, but it also depends on the query pattern. If the query pattern was, I just want information about Brian, then ultimately that data about Brian is going to sit in a single leaf. And the only impact that the 6 terabyte database had is I had to jump through 1 or 2 additional more hops before I got to that data. And once those hops get in memory, it's almost negligible. So if that were your only query, then actually these two queries, regardless of the size of the database, are going to be quite similar. But if the query was, I want to average every value in the database, obviously, if I'm running a 50 megabyte database, it needs to scan through 50 megabytes of data to create an average of everything. If I'm running a 6 petabyte database, it needs to scan through 6 petabytes. So the impact there is going to be monumental. So again, it depends on the types of queries and what's going on. It also depends on the rate of change of the data. So if the rate of change is low, more data ends up being cached in query servers. It depends on the memory you have for query servers. But those are all kind of things to think about or potential impacts that could be there. And that's it. That's all I have for this presentation. I hope for those of you, especially looking at running Fluree in production environments and thinking about ideal architectures and how to structure it, I hope this answered some questions. Also gave some insight into what some of those settings are that Fluree has and why those settings exist. We are out of time for today. Happy to continue the conversation on our Slack channel. You can join our Slack if you're not already there at this launchpass.com/FlureeDB, and that'll actually generate a invite to you for the Slack community. I encourage you to go there, and of course, developers.flure.ee is where our documentation is. It's just been revamped. It's got a great search bar in it now. So even if you wanted to search for some of these settings that we just talked about in this webinar, it's really easy to find those and get to those now. Appreciate your time and support. Thanks, everybody.